Hey everybody, welcome. It's me, your friendly neighborhood chemistry teacher. I'm here today in the lab to show you how to collect data for a lab on radiation. Now, you might not be studying radiation specifically in class, but this is still a good activity because you'll see some different types of graphs than you're used to when we look at the different relationships. And it will get you to understand how to write a purpose, how to plan out an investigation on your own, and how to write a good conclusion statement about your findings. So let's hulk out on this lab about radiation. Now, just so you have a little bit of context, I'll give you some very brief information about radiation and what we're looking at here with this experiment. Now, radiation is a very general term and covers lots of things that are both harmful and not harmful. Radio waves are technically radiation. Any light that you see is technically radiation. But what we are going to be talking about today is nuclear radiation, or radiation coming from a nuclear reaction. So while chemical reactions are what we normally work with in chemistry, things where atoms are rearranged or electrons are changed, we're going to be looking at a nuclear reaction where a nucleus is changed. I have some diagrams on here. The key is here that protons will be represented by a purple plus sign. Neutrons will be represented with a green 0 since they have no charge. And electrons will be represented by a pink minus sign. These are the only two things that really have mass and contribute to the mass of an atom. Here I've drawn a diagram of a radioactive atom called carbon-14. Carbon-14 is how it's written. This is not a minus sign, and this is how it's abbreviated. In uppercase C for carbon, the 14 is the same as the 14 here and represents the same thing. The 6 here is not always included because it's redundant information. If this is C, this has to be a 6. The 6 represents how many protons are in that atom, and the protons are in the nucleus. The 14 here and here represent how many total things are in the nucleus, because those are the things that add mass, and this is the mass number. And so you can see that carbon-14 has 6 protons in its nucleus, and because there are 14 total things in the nucleus, there would be 8 neutrons. Now I'm drawing a neutral version of carbon-14, and so electrons, because there are 6 protons that are positively charged, there need to be 6 electrons as well. Now, carbon-14 is not stable. What happens over time is that one of the neutrons in the nucleus actually breaks apart into a proton and an electron. The electron is so high energy it flies off into space, and that high energy electron is called a beta particle, and that radiation, that energy carried with it, is beta radiation. So here's what happens over time, that the carbon-14 turns into nitrogen-14. Again, the 14 meaning that there are 14 things in the nucleus, or its mass number is 14. The 14 here and here mean the same thing. 7, though, is what is changed, and that is the number of protons in the nucleus. And because there are now 7 protons, by definition, it is nitrogen. So now there are 7 protons, and because there are 14 total things, there are 7 neutrons. And nitrogen-14 is a stable isotope and would not undergo any more nuclear reactions. Here's a representation of it. Carbon-14 turns into nitrogen-14. This B, it's a Greek letter beta actually, is how a high energy electron or beta particle or beta radiation is represented. It has 0 because electrons essentially have 0 mass compared to protons and neutrons. The 7 here represented how many protons were in this atom, and the 6 here represented how many protons were in this atom. The -1 represents that this thing flying around on its own has a 1- charge, that it's nuclear charge because it doesn't even have a nucleus. Its nuclear charge is -1. Now notice that the numbers here in the upper left, on this side of the arrow, and on this side of the arrow, total 14. The numbers in the lower left in both sides of the arrow combine to form 6. And so those numbers are conserved. Mass and charge are conserved in nuclear reactions. Though the elements can change from one element to another. That's the difference between a nuclear reaction and a chemical reaction. This symbol here is a lambda, and it symbolizes what's called the half-life. The half-life of carbon-14 is 5,730 years, give or take. And what that represents is that if you have a sample that is all 100 grams or 100% carbon-14, in this amount of time, half of that sample will have turned into nitrogen-14. 50% will still be carbon-14. After another 5,730 years, the 50 grams remaining would be also cut in half, down to 25 grams. That's called exponential decay. These are the radioactive samples that you'll be working with for this activity, 3 of which came to us from a kit bought from a science supply company, and 1 I was able to pull these from some ionizing smoke detectors. They have actually a sample of this radioactive isotope, americium-241. All of these are not naturally occurring isotopes. They are typically formed from nuclear reactors or spent nuclear fuel, which they can then sort out and repurpose. Americium-241 is abbreviated this way, and in a reaction, it decomposes to neptunium-237. Now, when you look at the numbers and understand that they're conserved, you can see that it would give off this. This is an alpha particle. Alpha particles have a mass of 2 and have a charge in their nucleus of 2, and they're really high-moving helium nuclei. Alpha particles have a lot of energy in them when they fly off, but because they are so big compared to other radioactive particles, they are blocked easily by even something like paper. And so, while alpha radiation is very dangerous for exposed tissues, your skin does a really great job of protecting you. If, however, you were to swallow this, that would do serious radiation damage to your intestines and digestive system. And if any of the atoms got into your bloodstream, that also could be very damaging. The half-life is 432 years for this. We have another alpha emitter, and that's polonium-210. It turns into lead and releases alpha radiation. Its half-life is just 138 days, approximately 4.5 months. Notice that the sample here, the metallic polonium, needs to be exposed. It can't have plastic over it like the other samples, and that's because even the plastic would block the alpha radiation. For beta radiation, we have strontium-90. It has a layer of plastic over it, which is fine because beta particles or beta radiation can go through plastic. Strontium over time turns into yttrium, and its half-life is 28.8 years. To investigate gamma radiation, which is what this symbol is, notice that gamma radiation has a 0 and a 0. Gamma radiation is a form of electromagnetic radiation or light. It's incredibly high energy light. So cobalt-60 is what we have that emits gamma radiation. Over time, cobalt-60 turns into nickel-60. It releases beta radiation as well to do that, but it also releases gamma radiation. The half-life of that is 5.3 years. For this lab setup, I'm really going to focus on americium-241, though these are the other samples that are available to you. So I'm going to get rid of these, and we'll focus on getting set up with this sample of americium-241 that again was removed from an ionizing smoke detector. So here are all the materials that you're going to need for this experiment. You'll need a ruler, your radioactive sample, a ring stand, a radiation detector or monitor, a test tube clamp, a LabQuest Mini that the radiation monitor will plug into, and a USB cable for the LabQuest. The radiation monitor is going to be plugged into one of the digital inputs, and you're going to suspend it on the ring stand over your radioactive sample. And lastly, you'll plug in this so that you can go and plug this into a USB port on your laptop. All right, so now I'm going to show you how to get this set up on Logger Pro. Let me switch to Logger Pro. Okay, here we go. So this is what it looks like when you plug this in. It'll give you this setup where it'll be time and radiation counts. We're going to change this though. We're going to go here to data collection. And instead of time-based, we're going to make this events with entry. That means that every once in a while, we're going to have it collect data and we're going to record what we have changed. And so the column name, what I'm going to show you how to change, though you can choose other things, I'm going to choose that I'm changing the distance. I'm going to be measuring distance in units of centimeters. I'm going to change some settings on the probe itself, and that's up here with setup sensors. And I'm changing the count interval. So right now it would only collect how many counts were recorded or how many radioactive particles hit the detector for 5 seconds. I would suggest changing this to anywhere between 15 and 30 seconds. Now we're going to be ready to collect. What that's going to look like is you're going to hit the collect button. And after your interval that you had selected in the setting up the sensors, after that time goes by, you get the option to keep that point. And you would press that button, and then you would manually type in whatever it was that you would change. And so you could type in the distance, and you would measure the distance that the radioactive sample was from the detector. You hit OK. Now it's telling you that it's paused, and you change that distance, or you change the number of index cards that are in front of your radioactive sample. And whenever you've changed it, you are ready to hit continue. Now notice that I put the radiation monitor right on the sample, but I still counted it as being approximately 0.15 centimeters away from the sample. And that is because the detector that's in here has a protective screen, and so the sample itself cannot really touch the detector and get to 0 distance. And so what I was measuring on the ruler, though it wasn't clear from watching, is that I really, in my head, was looking at what was on the ruler and adding 0.15 centimeters each time. Then when you've collected enough points, you would stop collection. And now you can worry about how to format this. I'm going to auto scale to start off. I'm going to title my graph. And then I'm going to see what kind of curve this fits. I'm going to go up to curve fit. And what you can do is you pick general formats of equations and you hit try fit. So that does not look like it would fit well. What should fit for this type of setup would be inverse square. So let's try that. Doesn't seem like it's going to quite do it. That one also looks a little bit better, but not quite. So this natural exponent seems like it's going to be the best fit for the data that I have, though maybe I would have gotten a better fit or a different fit if I had selected more points. Now, when you're thinking about distance from the sample to the radiation monitor, and radiation counts, or amount of radiation, you would expect to see what's called an inverse square relationship. And that's because as this moves further away, you're going to get less radiation, and so that is the inverse piece. And it's an inverse square because if you were to imagine that this cone was representing where the radioactive particles are spreading out from, so they're all spreading out from this one point, and they would all spread out evenly. If you're imagining it that is the case, you can see that when the detector is lower, it can essentially collect all of the radioactive particles, and so would be collecting 100% of the radiation being given off. But as you move up, it's collecting less and less of a percent from that distance. Distance is measured as only one dimension, in centimeters in this case, but because the detector has a surface area, that's measured in 2 dimensions. Surface area is measured, it has both length and width, and so that's why it's an inverse square, because it's 2-dimensional space. It's a 2-dimensional surface that's collecting data when you are moving away or toward in 1 dimension. So that's a very basic setup for how to collect radiation data from a radioactive sample using LoggerPro and the equipment that we have from Vernier. What you're going to be doing, though, is not just collecting data from one source, but you're going to be changing some things, and you're going to see how 2 different things compare. You're either going to be comparing different radiation sources, or you're going to be comparing the same radiation source, but comparing maybe distance to number of barriers, or number of index cards, or various types of barriers that we have. And you're going to look at how those things affect the radiation count. You're going to come up with your own purpose, you're going to collect the data, and then you're going to write your own coherent conclusion statement about what you determined that relates to what you set out to determine. A simple purpose for this piece that I just did could have been that it's to investigate how distance and radiation count relate to each other when looking at a source of alpha radiation, like americium-241. I would have predicted that it would have been an inverse square law, but it seemed to be the natural exponent ended up being the best fit for those data. I maybe would have had something different had this been done in a vacuum, or had I got more points and made a smoother line. So you'll take your time to really try to get good quality data so that you can make some decent conclusion statements. So get to it and try your own things out.